Okay, so today we're going to take on the idea of implicit differentiation. All right, so when is implicit differentiation used? It's used when we have something where we want an instantaneous rate of change, but we don't have a function. So a good example here would be something like x squared plus y squared is equal to 25. This is clearly not a function. If I were to graph this, this would be a circle centered at the origin with a radius of 5, right? So I want a way to find what is the rate of change at any given point of that circle if I'm given x and y. Okay, so what I do here is I'm going to take the derivative of everything with respect to x. Okay, so got to use the chain rule here. So the derivative of x squared with respect to x is going to be 2x, and then I'm going to write the derivative of the inside with respect to x as dx dx. That's going to help me keep track of some stuff. I mean, in reality, that's equal to 1. So normally we just leave it off, but for implicit differentiation purposes, I'm going to leave it in. All right, so this is 2y, and then the derivative of y with respect to x is going to be dy dx. That's using the chain rule, right? And the derivative of a constant we know is 0. All right, so like we just said a moment ago, this thing is equal to 1. So I can make a quick simplification here. This is 2x plus 2y dy dx is equal to 0. Well, if I subtract the 2x from both sides, I get 2y dy dx is equal to negative 2x. And if I divide both sides by 2y, I get dy dx is equal to negative x over y. So this means that if I pick an x value and a y value that's on this circle, I can use this to find the instantaneous rate of change at that point. Okay, so this is a clever way to kind of find a derivative when you have a smooth non-function. All right, so this is fairly useful. We're going to look at an example of taking a second derivative because this gets a little bit complicated. Okay, so let's say we have x to the fourth plus y to the fourth is equal to 16. I'm going to need a lot of space for this. Okay, so I want to find the second derivative of y with respect to x. So the first thing I do is exactly what I just did before. I take the implicit derivative, 4x cubed dx dx plus 4y cubed dy dx is equal to 0. So everything's working just like it did before. This is 1, so we get 4x cubed plus 4y cubed dy dx is equal to 0. And this gives me 4y cubed dy dx is equal to negative 4x cubed, which implies that dy dx is negative x cubed over y. Okay, so that's the first derivative. Now, I can go directly from here to get the second derivative. I don't need to do this implicitly. The second derivative with respect to y, of y with respect to x is going to be low d high. Let me give me some room below here because this is going to be pretty big. Low, oh, that's cubed. There we go. Low d high negative 3x squared, right? D, okay, dx dx, right? So low d high minus high That's negative x cubed. D low, so that's going to be 3y squared dy dx. Fit that in there, right? All over low squared, right? So the low squared here would be y to the 6th. Okay, so let's simplify a little bit here. This is going to give me negative 3x squared y cubed. That's a 1, right? And then we have a negative and a negative, right? Which should make this a plus 3x cubed y squared dy dx over y to the 6th. But here's the key. This we know that dy dx is this, right? So we can make a substitution there. So this is going to give me negative 3x squared y cubed plus 3x cubed y squared times negative x cubed over y cubed, all over y to the 6th. Now, an interesting note is that if you are on a free response question, you can actually stop here, because at this point you actually have the second derivative in terms of x and y. It's sloppy, but it's there. I'm going to go ahead and clean this up a little bit. It's going to give me 3x squared y cubed minus 3, and then let's see, that's going to be x to the 6th y to the negative 1 over y to the 6th. We don't like having that there, that negative 1, so we're going to like divide top and bottom by negative y to the negative 1, so that's going to give me 3x squared y squared, right? Y cubed. No, take that back. That is, so we're multiplying top and bottom by y to the 1st. So that's going to be y to the 4th minus 3x to the 6th over y to the 7th, right? That's what I get if I multiply top and bottom by y. And I have all positive exponents, a nice, neat little rational expression here of x and y to give me the second derivative. So this is the second derivative. This is d2y over dx squared. All right, and shows you a little of the trick there that you have to sub in the first derivative that you found implicitly in order to make that work. All right, so that's the whole ball game. Thank you.